Welcome to our next lecture in the series on condensed matter theory. In this lecture I want to talk about an Hamiltonian in a periodic lattice and crystal momentum that we will find to be a good quantum number in such lattices. In previous videos we have seen that we can introduce an Hamiltonian, which is a sum over all momenta, and then the kinetic energy that we have of the electrons, plus an interaction between electrons at different momenta when the momenta difference is equal to a reciprocal lattice vector. They interact with v of q, and an electron can scatter from wave vector k to wave vector k plus q. And we've also seen that our periodic potential can be written as the Fourier transform of the real space potential, e to the minus I q dot r dr. So if we look at an example where we take a periodic lattice in one dimension with lattice constant A, and then we can plot our energy momentum dispersion. H bar k square over 2m if we do not have an interaction between the electrons. As a function of momentum and we find that we can define our reciprocal lattices as a distance 2 pi over a, such that we have a reciprocal lattice point at 2 pi over a, 4 pi over a, minus 2 pi over a, minus 4 pi over a, etc. And now there is an interaction between the electrons. If I have, for example, an electron at this wave vector, then it interacts with an electron at a wave vector 2 pi over a larger, and it interacts with an electron at a wave vector 4 pi over a larger, etc., or smaller, or 4 pi over a smaller, etc. So there is a set of states that interact with each other, but do not interact with all the other states. And the same is true for wave vectors at a different length. They interact with each other, but there is no interaction between my purple and red electrons in this case. So the Hamiltonian on a basis set of plane waves is block diagonal, such that the interaction between two states, k and k prime, is 0 when k minus k prime is not equal to a reciprocal lattice vector, and it is v of q, or k and k prime, when k minus k prime is equal to a reciprocal lattice vector. Now we're going to define the crystal momentum. For that we'll use k with 2 lines in there, and many textbooks will use the same letter for crystal momentum and the normal momentum of an electron, and we'll later see why this is the case and how equivalent crystal momentum is to the real momentum that you have. I'd like to make the distinction here, but in the end they become very similar in the way they function. Of course, they're not similar in how they are defined. Our crystal momentum will be defined to the momentum reduced to the first zone. So we will subtract reciprocal lattice vectors from our crystal momentum, and we can define that by taking the inner product of K with one of the lattice vectors and then take the positive integer part of that. So these brackets mean the positive integer part. So if this would be 3.1, you're left over with 0.1. If this is minus 0.9, you're left over with 0.1. Times the lattice vector B1 plus, and then the same for the other two directions given by the reciprocal lattice vectors. And two states interact if they have the same crystal momentum. States do not interact with each other if they have different crystal momenta, or states can interact if they have the same crystal momentum. So we can again draw an energy momentum distribution, but now not as a function of the real momentum, but as a function of the crystal momentum. And we look from 0 to 2 pi over A. And we see that we have here our quadratic dispersion. Then once we hit the zone boundary, we jump and we continue. And here the crystal momentum is the full momentum minus 2 pi over A. Whereas for the blue, the crystal momentum is equal to the momentum. You can of course also look in the other direction. Here I hit my zone boundary, I would have continued here. And this is now folded back to the first Brillouin zone, where the crystal momentum is the full momentum plus 2 pi over A. And this comes from the bands that we would have had over there that are shifted. Well, I can in principle go here and then even to the next zone, which would give me a band that is here, which is given by the crystal momentum is the full momentum plus 4 pi over A. The energies that we have as a function of crystal momentum, and now we need more quantum numbers, because as a function of crystal momentum I now have several energies, and for the case where the potential is 0, we can write this as h bar squared, and then we have the full momentum squared, which is the crystal momentum plus n1 b1 plus n2 b2 plus n3 b3 squared divided by 2m. So our wave functions are going to be wave functions as a function of crystal momentum n1, n2 and n3 as a function of r, or instead of writing 3 quantum numbers in here, which is only true if Vk is 0, we'll make them a function of crystal momentum and some quantum number tau. Now the function here that we have as a function of crystal momentum is asymmetric with respect to our crystal momentum. We took our crystal momentum to be positive. We can make everything symmetric by shifting the reciprocal unit cell. It does not necessarily have to be in the positive part of the set of wave vectors that we have. And we can actually define the reciprocal unit cell such that we take those vectors that are the smallest norm. So in our one-dimensional example, that would mean that we define the crystal momentum to be in the range from minus pi over a up to pi over a. And then we have 0 in the middle. And now our energy momentum distribution is again parabolic. And notice that we still have no potential in there. So I only took into account that we have the symmetry for our crystal. And we see that we have such kind of allowed energies in our crystal. So we have here epsilon as a function of crystal momentum. In order to label our states, we can label them by crystal momentum, but they're not uniquely defined by crystal momentum because there are infinitely many states at each crystal momentum. And we can use the band index for that. So the lowest band I'm going to call band 1, where band are all the eigenstates that we have. The second band I'm going to label with band number 2. And the third band I'm going to label with band number 3, etc. So we have now as an index, as a quantum number for our wave functions or eigenstates, the crystal momentum and the band index. And with that we can label all eigenstates, and of course for the case where our potential is 0, we can directly relate them to the eigenstates that we have, which are plane waves and the energy h bar squared k squared over 2m. In the next video I want to have a look what happens when our potential is no longer 0, what kind of interactions that gives and what kind of deformation that will give in the energy momentum dispersion relations. Thank you very much for your attention. Stay healthy. We see each other next week or in the next video.